Hello, everybody.
Just the last like 40.
So, it's good morning. I know. I didn't want to do the whole quote. I'm sorry. Out of respect. Out of respect. Okay.
Is there no
Glad to see all of you. It's wonderful. Thank you for worrying enough about your grade to come say hi to me one more time. So, how many of you do not have the sheet or a copy of the sheet somewhere where you can see it? For this first one, there's a lot of text involved describing just the constraints of the system. Just note that this one is more for testing your ability to go from text to a finite state machine. There will not be too much of this on the test. It'll be more like what I've got here, where there's a part where it's like, hey, design me a state machine. And then the other parts are, well, now use this one to do everything else. So that the mistakes don't all concatenate into each other and, of course, result in you getting a lower grade because you made more machine when you should have made a Mealy machine or something like that. So, I'm going to read the whole thing, and I'm just going to annotate the important parts. Make sure that you think they're important parts as well, because, of course, that's the important parts. So, okay, there we go. Can you all hear me if I talk at the board? In the back? You're good?
Yes.
Okay. Okay, so this one is a finite state machine design. It is inspired by Pierre Emmanuel. He is the teacher for embedded systems. Basically, one of his examples to prepare you for his midterm is similar to what we're doing here, but it's much more complicated in his class. So I've simplified models to make it a little easier for more of a test review setting as opposed to actually trying to prepare you for a midterm that's worth 30% of your grade. So, and half of Pierre's test was one finite state machine. So if you plan to move on with anything that has finite state machines, they will get more complicated because your teachers will typically want minimal states. We're not doing that. Do not try to minimize your states for this class. If you end up with 23 states, if it works, you're fine. If it doesn't work, then you'll be docked. In other classes that do finite state machines, most teachers, if you gave them 23 states when you could have done it with 2, will dock you points. In this class, that is not true. If it works, you get the points. Okay. So, in this finite state machine, I'm just going to read it again. This problem deals with designing and implementing a finite state machine for a water flow controller. The goal of the system is to create a specific flow pattern based on a 3-bit input. So we have some input due to 0 that I call target. So that's what I'm going to continue to use here. The system will consist of a flow sensor that returns a 3-bit value which represents the current flow speed. So we have some kind of measured value, and the goal of the circuit is to get target and measured to be equal to each other. Okay? I'm going to skip around in a little bit of that. There's also a 2-bit input called valve, I called it flow. This determines how much a valve is open. Of course, 0 is all the way closed, 1 is all the way open, but our system is not optimal. And I say this all in the problem, so don't worry, you don't have to assume this. Our system is not optimal. We cannot directly map an output from flow. So we can't give flow 1, 0 and then assume we're going to get like something like 1, 0, 0 out of measured. Our system is not optimal like that. Our valve might be a little janky, a little broken, might do different things depending on where it was before, etc., etc. So it's just not optimal, which means we need to increase and decrease, not straight up set. And then to make things even more complicated, which, trust me, this is still much easier than what Pierre gave us, the flow in this pipe is not consistent at all. Meaning, basically, we want to make sure that it's wrong 3 times in a row. If it's not wrong 3 times in a row, don't touch it. Don't adjust anything. So, we're looking for 3 consecutive failures. I also state in parentheses that after you adjust the valve, you must get 3 more consecutive failures. Trust me, this makes designing the state machine a bit easier instead of a bit harder, like it may seem. Okay, so part A is design a Mealy machine for the system described above. What is a Mealy machine? What do we have to ensure to make it a Mealy machine? So in a Mealy machine, you're correct. The output depends on the input, some kind of input, and the current state. In a Moore machine, the output is simply dependent on the state. Okay? So for a Mealy machine, we have to make sure that we design this so that somehow our output, which our only one here is flow, our output depends on our inputs, which means we will have fewer states but more complicated output logic. Okay, so first state we make in a finite state machine is, of course, the default. This is where it goes. If you want to be super technical about things, you'll put this little lightning bolt symbol here. This means that if we hit some kind of clear button or when we start up the circuit right at first, this is where we go. Now, in this problem, I do not specify to put in clear, so don't. If the problem does not ask for clear, don't put clear in as a button or an input or anything. Okay? Good. This one doesn't ask you to write code anyways, so clear doesn't matter. So, at what state do we move out of default, and at what state do we move back around into default? What's our condition for moving? It fails 3 times. Now, if we want to have a counter and count up to say we fail 1, 2, okay, now that we've failed 3 times, move out of the state, we could totally do that. Let's not. That complicates our logic a little bit. That means we have to do more than just state and output logic. That means we have to do timers and counters, and let's avoid that. I specifically made it 3 so that it was going to be easy to avoid that. So, let's avoid counters entirely. So, we want to move out of this state when we measure something incorrectly. So, what state are we looking for? Measured what?
Equal.
Capital T. So if measured does not equal target, then we go into some kind of, I don't know, I'd label wrong 1 state. We've gotten 1 wrong. Okay, there's going to be 2 ways out of this state, right? 1, if measured does not equal target. And of course, we've got 1 here that's if measured does equal target. Where does this one go? It goes back to default because we want 3 consecutive, not 3 total, right? So if we measure 1 wrong and then 1 correct, we're going back to the start. This is just because this worked, just because it's consecutive. If we wanted it to just work on 3 failures, then it would sit here and it would be circular waiting for another failure. So we're going to have some kind of wrong 2 state, and this state's going to do the same thing, where it's going to come out on measured does not equal target, and over here, if measured does equal target. I have some definitions farther down of just some just variables that you have access to. I have MNET and MGTT. MNET is measured does not equal target. This is to make it so that you can actually put it into a Carnot map and simplify it down, because it is a 1-bit value. So MNET just holds the result of measured does not equal target. So not MNET is measured does equal target. So I'm just going to start writing that because that's a lot faster to write. Now down here, how many times have we checked to get to this state?
3.
We've done our 3 checks, which means in this state, this is where we change things, right? Because we measured 3 incorrect values, we need to change something. So here, I'm just going to call this the change state. And we need to do something with our actual, by the way, if everyone could just move the monitors so that they're vertical so that people don't have to like look around the monitors, that would be great. Anyways, so we're going to change what based on what? We're going to change our flow based on our inputs, right? So we're going to have some kind of, let's see, MGTT. We're looking for if it's greater than. So if MGTT, then we've measured more than we want to get. Are we going to increase or decrease flow? Decrease flow, yes. And this is bad Verilog. This isn't Verilog right now. It's just pseudocode at the moment. And then, are we going to have an else if? Just an else?
Why are we doing this in this state instead of using another state? Transition space happens.
We could have it literally happen on a transition. Just for seeing purposes, we're having it happen in a state. So technically, we're losing a little bit of our precision here, but it doesn't really matter in this circumstance. So we're going to have some kind of, this is going to be just an else case because we've measured incorrect 3 times. Something needs to change. Even if, at this moment in time, we do happen to measure that they are equal. Basically, this is just, it was wrong. Let's make sure we adjust to where we need to be. So technically you would want to do an else if, but this is what we've got. Where do we go from this state? We just, on no condition, we go back to default. Period. This is a Mealy machine. What he was saying is that technically we would want to change on this transition so that we just go right back up to default. Yes and no at the same time. This is a lot easier to see and a lot easier to read, and this reads to a teacher, you know exactly what you're doing. It would get very cluttered down here if we had it just work on a transition. Mostly this is because of how we've been writing our state machines in this class. There is a computer science standard, there's an electrical engineering standard, and then there's this, which is the introduction. This is generally how it works. If you want to know the standard, circles are states, diamonds are conditions, and squares are output changes. It gets disgusting and it gets big, and honestly this thing would take up the whole board if I was to try to do it with the actual industry standard way to do it. So right now, just because, again, this is more of an intro to how these state machines work, that's how you're going to do it. Okay. At this point, we are mostly done. Technically, we should come in here and we should label what flow is going to be in each of these circumstances. It's going to be the same thing here and the same thing here. That's why I put it in blue. Just the blue follows down where flow stays what flow was. The only issue that we have introduced here is another issue that exists in part B. And that is that, well, what if we go into flow minus minus and we're at 0, 0? Then we wrap back onto 1, and now we're as open as this valve will get instead of as closed as this valve will get. So technically, we should add some kind of check, not only if if M is greater than T, but also if flow is not already 2 bits of 0. And we'd want to add the same thing on this else. So yes, it would be an else if flow does not equal 2 bits of binary 1, 1. Now we've prevented wraparound. So now we won't accidentally go from all the way closed to all the way open because we've subtracted, or the other way because we've added. Because again, this system is not optimal. Flow does not give us measured. We cannot map them. So if our flow can't give us measured, we need to have it give us as close to possible as we can. And yes, because this is a 2-bit value and this is a 3-bit value, to get some kind of intermediate value, flow is just going to have to sit here and flop back and forth to get close to where we want to be. Any questions? Okay, part B, I give you a state machine and I ask what's wrong with it.
I have a question. It's more just on like Mealy machines. Should we be studying those? Because we never had a homework on them or a lab, so I didn't know if they're going to be.
It's fair game because it's in the book.
Oh, okay.
Mealy machine again. Output changes on both the input and the state. I'll show you more the likes of what you'll be seeing in the test, because this is chapter 7 stuff, what we just did up here, designing a state machine. This is chapter 7. Chapter 7 is working with systems. There will be a text description to a finite state machine. It's not necessarily going to be anywhere close to as much of a text wall as mine was.
There's a good way to like make a Mealy machine just to make a regular Moore machine and then find the final state, or final 2 states, and kind of just combine them into one like if statement.
Basically, yeah. And so you have a Moore machine where you have some kind of split off where here we output z equals 1, here we output z equals 0. Instead, whatever this condition is, we output that condition instead. So if this was, on condition x, to change this Moore machine into a Mealy machine, we'd have a state where we output z is x. So again, this is a Moore machine because our output is a constant at every point in time. This is a Mealy machine because our output depends on an input. Okay, I'm going to draw this next state machine up here on the board real quick. I say the following Moore machine has been created for the above design. Why is it a Moore machine? Okay, so this is the state machine. Why is this a Moore machine and not a Mealy machine?
Outputs depend on the state.
The output is only dependent on the state. None of the inputs appear in our definition for flow here, right? None of our outputs are there, so it's a Moore machine. Or sorry, none of our inputs are there. We can access the output and have it still be a Moore machine. Just so long as none of our inputs are directly affecting the output, it's a Moore machine. Okay? Why is it wrong?
We don't have a case for if by the time we get to the 3rd state, like the flow is equalized.
If it's been equalized here,
Well, so we check if it's greater than, we check if it's less than, but not if it's equal.
that's right here. Hiding off to the side there.
Kind of like we were talking about before. If it's already at the bottom, you can't close it more.
Yep. So one of the issues is it's just flow equals flow plus 1. Again, we want to make sure that we don't wrap from full to empty or from empty to full over here. So we want to make sure that if it is 0, we don't try to decrease it, and if it is 1, we don't try to increase it. There's one more problem with this state machine.
Do we need a line going back into default?
No, that's what that one on the left is. All of them are pointing into a line that goes to default. We're checking 4 times, not 3. Here's 1 check, here's 2 checks, here's a 3rd check, and here, getting into decrease and increase is a 4th check. The issue with a Moore machine is that you will have 1 less state than you think you'll have. Your actual comparison needs to happen during your 3rd check is when you need to be able to transition into increasing or decreasing. So the way to fix this is to remove one of the states. In my example, I suggest removing wrong 2, just completely removing it. This comes down to here. So now we check once, we check twice, and on the 3rd check is when we move into decrease or increase. Tricky, tricky, tricky. More machines have less states and more states depending on where you're looking at it. Because again, we want this, and then, oh, there's our 3rd check, and this is where we split, right? No. We split on our way into where the Mealy machine does its thing. Okay. Any questions? Going once, going twice. Sold. Part C is, even though the state machine is incorrect, create a state table for the diagram to the right. So, even though we're wrong, let's make this. So of course we need all of our current states. So we're going to have default. We're going to have ROM 1, ROM 2, compare, decrement, and increment. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What have I done? Oh, okay. And now our next state. This is where things get a little complicated. What is our next state based on? It's based on not equal or equal, and also on less than or greater than. We're going to write this a special little way where I'm just going to say that I'm going to tie some of these variables together. Let's say that W is equal to me tying in M does not equal T with M is greater than T, just like that. Which means we're now going to have W equals 0, 0, W equals 0, 1. And just to make this a little easier on ourselves, I'm going to put it in like a Carnot map. So we have 1, 1 in the middle. That way, when we transfer to a Carnot map, it'll be a little easier for us to see it because we won't have to jump around. And now we have our outputs over here. And these ones, again, because this is a Moore machine, and this is the official definition of a Moore machine, there's only 1 column in output. Okay. So, what determines if we move out of default? M does not equal T. So if our first bit is 1, we're going to move to wrong 1. Otherwise, we're going to default, right? We're going in a circle. And it's the same condition for the next one, to get into wrong 2. But remember, on equal, we don't stay in wrong 1, we go back to default. So this one's default as well. W2 has the same thing, but it goes to compare. Compare also has the same thing. And decrement and increment always go to default, right? Only one we have left is out of compare. So I've defined M is greater than T, so the MGTT value is 1. So when it's greater, we go to decrement. When it's less than, which means it's not greater and not equal, then we go to increment. Almost done. In default, we stay in flow, except for when we get down to decrement, where, of course, we output flow minus 1. And increment, where we go to flow plus 1. Are we done with this state table? Yes, there's nothing more to put down. Anyone have any questions? This one's a decently simple state table. Not much going on here. Okay, now part D is use the state table from part C, using the state table, so using this guy. Use Carnot maps to simplify the state transition logic for the second and third bits of state. Note I said second and third bits, that is bits 2 and 1, because the first bit is 0 aligned. So we're looking for, I like to use P to represent my state. That's just because S is representative of set. So I use P, so we need to get P2 and P1. P0 isn't terribly interesting, there's not too much to simplify there because it just kind of toggles here and toggles there. So, what is our first step? First step from a state table to a Carnot map. Gotta encode it. I've given you guys an encoding. So I'm gonna erase this and still put a little tick tick. Default is 3 zeros. So I'm gonna replace all of those with 0, 0, 0. Okay, W1 is 1, W2 is 2. And then compare is 3. Decrement is 4 and increase is 5. Okay. Do we need to change anything else? Nope, because all we're doing is the state base. So we don't even need to look at output and try to do any logic for that. In fact, if I were to have you put this in, I would have you put it in with an ALU that adds or subtracts 1 depending on how things work. I'd give you a block that does it for you. You just wire it in and pull the wires out. But because we only care about the states, we don't need to look at output anymore. So, let's go through and let's fill out the Carnot map. Can anyone tell me why this Carnot map is going to be super scary? As there's a 5-input Carnot map here now. In fact, 2 of them. I promise you they're simple. Just trust me on it. Because of all the states where everything goes to 0, a lot of this has been simplified. I believe I might have done this wrong in the solutions. Give me 1 sec. And do it again. Okay, and I'm just not going to write them again because they're the same thing as what's on the left. And this one is P2 is 1. Okay. Remember, P is our state. So from state 0, which our states are vertical in this map because the P1 and P0 are here, and then P2, 0 is there. So we have on our vertical, on 1, 1 and 1, 0, the only bits that's changing is bit 0. We don't care about bit 0. Which bit do we want to do first? Let's go with 2. Let's do the top bit first. The only place it matters is in 1, 1, where we have a 1 here and a 1 there. Everywhere else here needs to be 0, because the transition needs to go to having this state be 0. Okay, over here. From those states, they all go to 0. What do we do with the rest of the states that don't appear here? They don't care. So we have no way to get to them, so we should have no way to actually do whatever transition this happens to encode. Okay. Technically, this is one circle. How do we circle it? So we've got this one, but that circle's also over here on the other map. So that means this is going to be P1, P0, P2 doesn't matter because we're across the map, and M is greater than T does not matter, so this is and M does not equal T. And that's P2. Simple as that. Just remember, if you can do the circle on the other map, make sure you do. There are a bunch of places in homework 4 on those ones that you could have done, even though it was minimal on this map, it was don't cares on the other map. Or there were ones also on the other one. It was tricky because in your homework, it was this. And this circle is here, this circle is here, and you have the big one that you've already circled. So these two were cross map. Anyways, be careful with 5 input Carnot maps. Again, if you can circle it on the other map, make sure you do. Anyways, that's P2. Let's not redraw the entire map, shall we? So these are going to be don't cares still, and I'm going to come through and I'm just going to erase the zeros and fill them with ones where they're necessary. The second bit never gets set. When we're in 1, our second bit gets set on the bottom 2. When we're in 2, our second bit gets set when we're in 3, it does not get set, 4 does not get set, 5 does not get set. That's all we got to do. So how do we circle this? Well, we got this circle, which we can't do on the other map, and we have this circle, which we can do on the other map. So P1 is P1 not P0, and again, this is where P2 is 0 as well, so we have a P2 not, because this one's not across the maps, and then M does not equal T. And then P2 is 1 right here, but we're across the map, so we have or P1, P0 not, M does not equal T. And we're done.
Hold on,
2.
Does your bar extend P1 and P naught right there? Or is that just, no, first term?
This one. No, there's two
Okay.
different bars there. So one on P2, one on P1.
Okay.
Because remember, if you connect these bars, you've nanded them, not anded the not of them. Any questions? You likely will not have to fill out a 5 input Carnot map on the final. But if you do, I promise you it'll be more like this, where it'll be just a couple simple little states here and there. That should be pretty quick to fill out. You also shouldn't have to draw it if you have to do it, which saves a lot of your time. You'll just have to fill it out and use it. Okay? Now, this was system design. Again, this was take a chunk of text and put it into Verilog. Or sorry, put it into a finite state machine. That was part A. Part A likely won't have too much on the final because that is chapter 7, and you guys just barely touched on 7. You didn't do any homework on it or anything. The rest of this deals with stuff you have seen from chapter 6. So part B, which was, what's wrong with this? That's also technically systems. C and D you should know how to do. For certain. A and B, if you struggle with it, we haven't taught you it very well. So you probably should struggle with it. But just get a couple more practices in getting from text to state machine. Any questions before I erase the entirety of this board and move on to problem 2? Going once. Going twice.
The final is cumulative, right?
The final is cumulative, with quotation marks. Doing finite state machines, you will use everything that you had in this class. The reason that I don't have any like weird vocabulary questions or anything like that is because most of the vocabulary has already been established at this point in time. The only really weird vocabulary style question I have is one hot assignment. We'll get to that in just a minute. But it is quote unquote cumulative. And again, that's just because finite state machine design uses everything we've learned up to this point. So you should know how to do it. Okay, number 2 is use the following state diagram for the following question. So I'm just going to put it over here, and I'm just going to leave it up. Okay, this is more like what you've been seeing, especially in class and just simplifying down state machines and stuff like that. So, part A is this a Mealy or Moore machine? It would help if I put on the outputs, right? So, based on if what I'm writing, Mealy or Moore? This is a Moore machine because Z is only dependent on the state. Z is being set to a constant value based solely on what state it's in. If I had somewhere like where Z is X, now this is a Mealy machine. But because, again, Z is being assigned to 0 or 1, and we know what it's going to be in each state, that's a Moore machine. B, create the following circuit in Verilog. Here's the very important part. If you take nothing out of this class and you're planning to move to 3710, other than one thing, take this. What inputs do we need for this finite state machine?
X and Y.
X and Y, okay. Anything else? Clock. There you go. It's a finite state machine, it needs the clock. Any others?
No.
Nope. Okay, move on to outputs. B, anything else?
Nope.
Nope, everything else is internal. What internal variables do we have? Forgot clear, but I didn't tell you to put in clear, so you don't have to put in clear. We're clear. Right? If I don't tell you to put in clear, don't put in clear. Okay. What are our internal variables here? Yes and no. I'm going to do it a little differently. I'm going to do it the way that you should be doing it in 3710, which does not use next state. I'll show you how to do that in a little bit. So we have some register state. It has to be a register because we are assigning it within an always block. Even if it's an always at star, it has to be a register. Okay, we need to initialize it to something. I didn't tell you where to initialize it, so generally you'll just set it to 0, whatever 0 happens to be. Anything else we need to do before we start putting in our always blocks? Someone set parameters? Yes, we do. So A is 2 bits 0, 0. B is 2 bits 0, 1. C is 2 bits 1, 1. D is 2 bits 1, 0. Okay. Anything else we do before we move into always blocks?
Question. So Broombond doesn't want us to be initializing stuff in the top module like that. I don't know, like our Nexus boards are super special and have like a secret reset button, but not everything does. So if we want to set that to be 0, where do you want us to do that instead?
If Eric specifically asks you not to initialize, then you have to have clear. And you have to press clear before your board will work. Our boards are not that kind of board. There are a lot of boards out there that don't, that you do want to make sure that you hit clear before you start. This is not one of them. He's preparing you for stupid boards.
But am I going to get docked on the test if I do that?
Specifically did not tell you to add clear. Give me 1 sec. I actually do have to take this call. I've gotten it 3 times. Something might be happening. I'm sorry.
I got one today. My phone, it's like, if there's a weird number, it'll say like possible scam. And I ignored it after I said
One hot stick.
What, your phone comes
I don't
up
know
on
that
the
is.
first one? Mine says
Dude.
possible free cruise. They always intro like,
I'll get you to go. That's
Our resort. Which one's that? Goodbye. The one you stayed at.
I got
keep
one.
pressing.
I got one the other day. Like, she started going into her spiel. I just cut her off and I was like, did you realize these numbers on the national capital industry and you're now subject to a $10,000 fine? And she was like, oh, I'm so sorry, sir. We'll take you off the list right now. I'm so sorry. She was like,
What resort? The one that you were in class last week. I just wanted like, that's good. Did I ever tell you about the one that they called me and threatened to take me to court because
those are the best.
Oh, yeah. My student loans?
Yeah, those are the
Do
best.
you realize you have 20,000?
No, I did.
I've been hoping you were
I humored him for like 20 minutes. So you have to give me your credit card number so I can pay it off right now. I'm like, I don't have one. Can I use my mom's?
And they're holding it.
I literally done healthcare. Yeah.
They want you to get iTunes cards.
I'm only 17. How can I take on debt?
Okay, I'm back.
I've been hoping for one of those. They're like, we're gonna send the police over us.
That's right. We'll send the authorities. Cool. 2 hours. I'm home. Anywhere to stay.
Okay. So, what goes in and always at pause edge clock? And what goes in and always at start?
The other stuff.
So, always at start. Yes, this is where some of your next state logic would be. In 3710, if you put your next state logic and your output logic in always at star, you would have like nothing in your pause edge clock. If you did not do this in your UART lab, learn it now. State progression is easier, especially when you have timing. State progression is easier to do on the pause edge of the clock, as opposed to assigning a next state and then always its start. That is just to make sure that when you do your timing, you are only changing state at the exact moment you would like to.
It seemed like in the book, for not the UART lab, but the assignment before that, the book explicitly like did an example where you did one for your next state and the other for your current state stuff. So that's like not convention.
That is not convention. Convention is to put it in pause edge clock. So what you could have done for UART is some kind of, you have a counter that goes up and then you case on your state, and then if you're in state 1, if counter is 7, then next state, then you store next state in your state. You could totally have done that. This way is messier and harder to follow. Especially when you start writing, like, I don't know, an entire core for a processor in 3710. Yeah, no. You'll want to put a lot of your state diagram just pause edge clock. This is where you'll want to actually do your state transitions. So that's what we're going to do. And that's what's also in my answers. If you literally took my case statement out of here and integrated it with the one in here with a next state instead of just assigning state, that would work just as well. But it would be a lot messier because you'd have like everything in always at star, and the only thing that would be in the pause edge clock is state equals next state, because there's no timing or anything in this one. Anyways, let's make this happen. So our state transitions, again, I'm going to put them in here. We're going to case on state. On case A, what do we do? Move to B. So if X, state goes to B, else state stays at A. Technically, we don't need to put it down because if we don't put it here, it's implied that it's circular. Okay? This won't move out of state A until X is 1. So until this one condition is met, it will loop. Okay. So now we can go into B. What is B? What do we do in B? B is a little special. Just advance to C every time. No conditions, no if, ands, or buts. Just move to C.
Yep.
And we're done. On to C.
Hey, Xavier?
Yes?
Is that because, like, look, going back to case A, is that because A, there's a loop
The
going
loop
back?
for the X naught, yeah.
But B, there's nothing other than the advancement?
Yeah. B, just there's no condition, it follows this arrow out.
So I wasn't sure about that, because I wasn't sure if that Y was also on that line as well.
No, the Y is just this one.
Okay.
Every line gets its own label.
Okay, that will be true. Okay.
That does make it a little tricky to see, but every line gets its own label.
Okay.
So count the labels, 1, 2, 3, 4, 5, 6, and there's 7 lines. So one of them doesn't have a condition. On C, on condition Y, we move to B. Else, on condition not Y, that's a terrible Y, not Y and X, we move to state D. Question, is there a point where we can move to state C? Is there a circular transition on this guy? The reason I'm asking is because, yes, there is. There's a state, there's a condition that is not listed. What if they're both 0? Then we don't follow either of the conditions, which means we have an implied circular case. That is simply because, again, the 2 arrows that come out of here do not contain this condition. If it's not written,